Today, the main goal is to be able to calculate areas bounded by curves. And it's more than just area under the curve, here's the integral. We actually want to do things where we have physical shapes and we have to set up the situation. So we're going to look at many, many types of examples, because where we're going with this is we're going to then take these areas, next day, rotate them around a line to create a three-dimensional object that we can find the volume of, or the surface area of, or other things. So we start really, really simply. So I do know the following is true, because this is how we set it up to begin with. Okay? There's A, there's B, there's y equals f of x. I want the area, quote unquote, under the curve. What that means is the area from the x-axis to the curve. And if the curve's above the x-axis, it should be a positive value. If the curve is below, it should be a negative. I want this, so I know the answer is this. Great. Okay? That's a piece of cake. That's what we've been doing for the last couple days. That's certainly not the only problem that we can do. So, what if I want this area? Well, that's a little more complicated. Let me remind you of something you already know. You've done this before. I want the area between the circles. One is a circle of radius 5, one's a circle of radius 15. Oh my God, that'd be so I gotta section this off and do all this crazy stuff, or is there an easy way to find the area between the circles? What do you think?
Area with the big one minus the area with the small one.
So, wait, you're saying this would work? Do you agree with him? Yeah, it's the O duh. Well, I know this is the area under the blue. What is the area under the red? Wouldn't that be A to B of G of X? Mm-hmm. And I want the area between. So how about if I take the big and I subtract the small? Is that kind of the O duh? I want that to be absolutely an O duh. So when I'm finding areas between things, it usually means take a bigger one, subtract a smaller one, if that works. So it seems to me, oops. Seems that this would work fine, but that's still two problems I'd have to do from beginning to end. But they have the same limits of integration. And don't we know that the sum of the integrals is the integral of the sum, and the integral of the scalar multiple is the scalar multiple of the sum? Is there some way I could manipulate this and say that? What do you think?
Yeah.
Stare at that for a moment. Do you believe that? Yeah, because if you want to think of it this way, this is plus -1 times this, and then I'm adding. Yeah, this is way better. I'm only doing one integration. Is it possible some of the terms in f and g can combine or cancel even? Sure. So could I have started with this? Yes, and this is what I'm going to show you today. So when I'm doing this problem, I want you to think Riemann sum. And so here's what we actually do. I'm going to subdivide it, do all my rectangles, all this stuff like we did before. And what I need to do, let's say that's the one. I want to find the area of the ith rectangle. Remember there's the first, the second, the third, and so on. So wouldn't that be something about, you know, f of xi, f of x, all that kind of stuff? What's the height of this rectangle? Wouldn't the height be f of xi minus g of xi? Wouldn't that be the height? Mm-hmm. And the width would be delta xi. So that'd be the ith area. This is the trick, whether I'm finding an area, a volume, a surface area, an arc length. Later in Calc 3, when we do all sorts of three-dimensional things, it's always the same starting point. Find an arbitrary piece, describe it, And I'm going to show you the steps to take and then the steps we can skip, actually. So now I can say the area can be loosely described as the sum of all of those. I'll write it like this. You guys just did something like this the other day. So now the area equals, okay, this is so long-winded, but it's true, the norm of the partition, okay. You're gonna like this next thing. Now, do I know that's the definite integral? Do I know this? Yeah, you just turned in a quiz the other day where you told me what the definite integral was without evaluating it. So there's my definite integral. Here's what I want to do. This is sort of a general thing here. I want to describe an arbitrary piece. And then the next thing I want to do is that. Once I understand what the path is, I found an arbitrary piece, I then added them all up, then I took the limit of that sum, then I took that limit and defined it as a definite integral. But doesn't the definite integral look exactly like this? So once I understand the process, can I skip the process? Yes. I called this a stepping stone. Right? The summation and then the limit was a stepping stone to get to the integral. Our goal is, given the statement of the problem, I want to get to the integral as soon as possible. But you're going to find the majority of the problems, you cannot go from the statement of the problem to the integration directly. Most of the time you won't be able to do that. You've got to set it up because it won't always be entirely obvious, but once you figure out what it is, it becomes fairly simple. So, let's do an example of this. So I want to find the area of the region bounded by y equals 36 minus x squared, y equals x equals -3, and x equals, how about 4? Now, this is where it's very wise to draw a picture. Part of the reason you did all the graphing concepts is so you'd know how to recognize graphs. Not necessarily physically draw one, but you had a pretty good idea. I need to draw an accurate representation, something that looks like it. It doesn't have to be perfect. Most importantly, I need to get the correct curve on top, bottom, left, right. I need to have my boundaries very obvious. If my boundaries aren't obvious, I'm in trouble. Okay? So if I'm to draw this thing, well, y equals x, that's an easy one. 36 minus x squared. And how about x equals 4? Probably about right, I'm about right there. And x equal, what was it, -3? Probably, about right. Okay. Is it a perfect picture? No, but I got everything kind of where I need to have it. Do I have an enclosed region? Is there something that's completely enclosed? What do you think? I have a curve and 3 lines, basically. Well, if I go this way, this is open-ended. That's open-ended. That's open-ended. That's open-ended. But I think, let me use red. I think that this does that look like an enclosed region? There can only be one. So it looks like my answer is going to come from there. Now, here's the nice thing. As I move left to right, if I draw an arbitrary rectangle, I'm going to draw an arbitrary rectangle here. If I go all the way to the left to all the way to the right, isn't the bottom curve always going to be the line and the top curve always going to be the downwards parabola? Is that a good thing? That's a great thing. That's an absolutely great thing. So that means it's very easy for me to describe this. Okay? And by the way, I'm going to show you in a moment, you can always go sideways too. But if I go sideways, my boundaries change multiple times, so I don't want to go sideways. Too much work. So the top curve is the y equals 36 minus x squared, and the bottom curve is y equal x. So if I said, what is the ith rectangle? This one right here. Then it would be 36 minus xi squared, because it's the ith value, minus xi times the width. And what is the range of values for x? X is going to range from what to what?
-3 to 4.
-3 to 4. The key is, if my picture is even semi-accurate, I have everything in the right place. It's not perfect, but I have everything in the right place. My top curve is always going to be the same. My bottom curve is always going to be the same. So therefore, it's fairly simple to say, if I subdivided this into n rectangles that are all vertical, and I added them all up, and then I took the limit, I'm going to get the integral. We want to go directly to the integral, can we? Yeah. What's it going to look like? It's going to look like that. So do you see what we did? We skipped all of the Riemann sum. We always start with an arbitrary slice. And by the way, you never want to skip that step because you can end up making mistakes if you do that. So we start with the arbitrary slice. Those terms did not combine, those terms did not cancel, but sometimes they do, depending on my boundaries. Now, is this easy or is this complicated? It should be fairly easy. It's a polynomial. Is there any symmetry involved here? Remember last time we talked about symmetry? Do I have symmetric limits?
No.
No. So it really doesn't matter. If my limits were symmetric, then we would look for symmetry, but they're not. Okay, I said that's not the regular thing. It's just when it happens, it happens. So let's do the antiderivative. And get out your calculator. So what's the antiderivative? 36x
Minus x cubed over 3.
no, minus a third x cubed
Minus x squared over 2.
Yes, I will never put a variable in the numerator of a quotient if the denominator is a number. You always want a fraction. Why? Because otherwise you're going to screw up when you check. If you write a quotient and you check through differentiation, you have to use quotient rule. There's no exception. There's no such thing as a quotient that is not subject to quotient rule. But you don't have a quotient, you have a fractional coefficient. You actually have a product. There is no such thing as a quotient where your denominator is a number. That's not a quotient. Right? The number 1/2 is a number. It's not a quotient. X over 2 is a half x. It's not a quotient. Right? 2 over x is a quotient. That you have no choice. You know, I'm saying this in simple terms. You don't ever want to put this in a quotient. You will mess up when you differentiate. How do I know? I've seen it. Not you, but the person right next to you. All right, put in a 4. Calculate that at 4.
114.6 repeat.
No, don't. You have thirds. Don't give me a decimal. Gosh, come on. You have a fraction key. Use your 344 thirds minus, and now evaluate this at -3.
Negative 207 over 2. Minus negative 207 over 2.
Negative 207 over 2. So now when I put that together, what am I going to get? Probably something over 6, I'm guessing.
(1,363 over 6).
Now, if the numerator had a multiple of 2 or 3, my fraction key would go ahead and reduce that. Can I do the whole thing in my fraction key without ever even hitting equals till the end? Yeah. But you got to use parentheses. A lot of people don't like it. I would just go parentheses minus parentheses equals. I'm lazy. Okay. Now, remember the trick I showed you guys the other day? Can I do this without using my fraction key? Yeah. If I did all of this just straight up, this divided by, minus this, divided by, equals, I'm going to get an icky looking decimal. But don't I already know the denominator of my answer is going to be 6? Don't I see that right here? So take your icky decimal, multiply it by 6, and you have your numerator. That's the really, really short way of doing it. That's the answer no matter what. Okay, was that complicated? Not at all. Now let me give you an absolute mathematical statement. every area problem that exists, you can set up with horizontal rectangles. And you can integrate, therefore, with respect to y. It's not always a good idea, because in this case here, my boundaries would change perhaps too many times. So a simple rule of thumb is, if your boundaries are described as y equals, in other words, literally y is a function of x, then vertical rectangles are easier. It just makes more sense. Does that make sense? So you go with what the region looks like. But it may be the case that horizontal is better. And we're going to do every version today that you can think of. All right, so let's do another one. Find the area of the region bounded by, and that's the usual language we use. Y equals x squared and y equals, excuse me, and y equals, how about x minus 2? Let's see. Oh no, I'm sorry, x plus 2. X minus 2, what was I thinking? Yeah. All right. Over there I gave you a whole bunch of stuff. Did I give you enough information? Did I leave anything out? Well, I didn't tell you what values of x to use. Oh, well, this is all I had. I was reading this problem and it looked really interesting and cool, and is there enough information here? What do you say we draw it? All right, y equals x squared, looks like that. Y equals x plus 2. Oh, did I give you enough information? Yeah. Is there an enclosed region? Yeah, I just didn't tell you exactly where. Well, you think I need that point and that point maybe? That'd probably be wise. How am I going to find them?
Something equal.
The trace key on the calculator.
Well, I guarantee you I can find it a lot faster than that. Yeah, the trace key of my calculator I'll probably get really darn close to, by the way. Probably won't get it exactly. How would I find it? You said set equal. Set what equal?
The equations, the functions. So x squared and x plus 2.
When are these exactly the same? When x squared equals. Oh, okay. So let's set x squared equal to x plus 2. I don't know what to, oh wait, what if I do this? Would that make more sense? Does that factor? Here, I'll do my part. I'll even go that far. Will that work? Multiply it out just to make sure. So it looks like I have two possible values. What are they? -1 or
Positive 2.
positive 2. Let's see. Oh, I think that's my -1, and I'm pretty sure that's my positive 2. Okay, great. What's the y value? Technically, do I even need to know the y value? No, but it would be wise to check, because is it possible I made an error? Well, okay. It's possible you didn't make a mistake, but the person immediately to your left and more or less the person right behind them. Is it possible to make errors here? Yeah. I might have the signs on the wrong term. Does anybody ever make an error here factoring? Occasionally. So if I've got the signs on the wrong term, these won't work. So here's what I'm going to do. When x is -1, y will be the square of -1, which is 1. Y will be -1 plus 2, which is 1. Right, minor rejoicing. It's the same value on both. It means I did it right. When x is 2, y will be 2 squared, or 4. Y will be 2 plus 2, or 4. Okay, good. Yeah, I'm going to find them just to ensure that I actually have the right points. Now, I could do vertical, I could do horizontal. Vertical makes more sense because I can get away with just 1, but also because both of my functions were defined y as a function of x. So I'm going to draw an arbitrary rectangle. And do you agree, if I if I filled this up with rectangles, all of my rectangles have the line as the top and the curve as the bottom. Do you agree with that? That's what I need to see. My boundaries are not going to change. They're all going to be exactly the same. They're going to be line on top, curve on the bottom. And I'm going to be able to see that by just drawing one. As I move left to right, that's not going to change. So my ith area is simply the top curve, which is the y equal x, y equal x plus 2. So I'm going to have xi plus 2 minus the bottom curve, which was squared delta x. And what is the range of values for x in this case? -1 to 2. Why is it important that I write that down? Is that important to the problem? Or are we just writing it down because it's cool? Okay, it is cool, but is it important? Yes, it's going to be my limits of integration. So I need those, because if I don't have those, then I don't have these. So I write those down. Can I go from this directly to the area? This is the area of the ith rectangle. This isn't the answer to the question. It's that area right there. But I want the overall area, which requires that I add all of these up and then take a limit and so on. I want to go directly to the integral. So my integral looks like x plus 2 minus x squared dx from -1 to 2. This is why the picture is so important. If I try to do this in my head, is it possible I could subtract in the wrong order?
Mm-hmm.
Yeah. In fact, that's actually a very common error. But the parabola is way higher than the line. Well, eventually, yes. But not in the region that I need. So let's do this.
Half x squared plus 2x minus 1/3 x cubed from -1 or -1 to.
At first, there are a lot of common errors that occur, and all of them are easily fixable. But one of the most common errors, certainly for a little while, is that when we evaluate, we sometimes subtract in the wrong order. You always evaluate at the top one first, and then you subtract the evaluation of the bottom one. If you do it in reverse order, you're going to get the opposite sign. Is it possible for an integral in general to be negative? Yes. Is it possible for my area to be negative?
No.
No, I set it up in such a way that it has to ensure a positive answer. I clearly see a physical area there. What if I got an answer of 0? Would that be bad? Yeah. Because I'm trying to find, you'll be like, I'm going to weigh you, Austin. I keep getting 0. Oh, yeah, I guess you are weightless. No, I probably did something wrong. I should be getting a positive number in the end. If I'm not getting a positive number, something went wrong. What you don't do is you don't fudge it. I got -10, oh, the answer must be +10, I'll just fudge it. Well, no, it might be -10 because I made an arithmetic mistake. I literally make a bad calculation. So always go back and redo it to make sure. Okay, on your calculator, can you do the entire thing in one step? Yeah. Do the whole thing, use parentheses, the whole thing, minus parentheses, the whole thing.
9/2. 9/2.
9/2. See, I would much rather you just tell me the result. I'm going to make the assumption that you are doing the whole thing on your calculator. I don't really need to see you tell me, and 1/2 of 2 squared, that's 2. And then 2 times 2, that's 4. I'm having fun because I'll have people tell me every single arithmetic step, and then you're going to re-enter all those numbers. Just do them all one time. If your answer is rational, give the rational number. By the way, would it be correct to say 4.5 in this case? Yeah, it's a terminating decimal. There is no scenario that exists where you ever approximate a fraction. You don't approximate a third, you write a third. By the way, the word approximate doesn't even apply to fractions. It only applies to irrational numbers. You approximate irrational numbers because you can't give an exact decimal value, but you can for fractions. So unless you want to figure out what the repeating sequence and put the bar, that's inconvenient at times, just leave it as a fraction. Now, 9/2 is a terminating decimal, so there's no loss. I teach statistics and we run into this problem all the time. People don't know when to approximate versus when not to. If my answer has to be a decimal value, I'm in a chem lab, right? I'm in a physics class, I have to give a decimal value. Then I need to take my numerical answer, throw it on the calculator, and give you a decimal approximation of the numerical value. But always start with the numerical value. So in the previous example, this is the answer. But if I'm in the physics class or the chem lab, I may need a decimal value. Well, that's easy enough, because I have that value in order. But generally speaking, you really don't have reason to approximate the fraction because it's a fraction. It's already nice. Okay, so far so good? So what if, a really simple one, I have something like this. I have, how about, find the area of the region bounded by y equals the inverse sine of x, y equals pi over 2, and x equals 0. Okay? I know what a sine wave looks like. Let me remind you of something that you learned as mathematical children. Let's say I have, here's y equals f of x. Can you tell me what the graph of the inverse function, and that's how we write inverse, the -1, like inverse trigs. Can we tell me what the graph of the inverse looks like? Do you remember how to do this? If I draw the line y equal x, it looks like the mirror image. So whatever that one was, probably something like, I know it's not a great picture, but you get the point? Whatever your original function is, the inverse looks like a mirror image over the line y equal x. Why? Because every point on here that looks like a comma b has a point here that's b comma a. X's and y's switch places. That will be useful for trying to figure out what an inverse sine graph looks like, because I know exactly what the sine function looks like. I can do that one pretty well. Let me do it over here. Because for me to find this area, I have to know exactly what the region looks like, because I don't know where top, bottom, left, and right are otherwise. All right. Well, a sine wave, I know, you're right, it goes like this forever and ever and ever. But remember, for the inverse trig functions, we restricted the domain. So let's go back to that. What did we restrict the domain to? And remember, just from here to here. Right? Do I have a horizontal tangent at that peak? Yes, I do. So if I flip this over the line y equal x, then shouldn't my inverse graph, or this has a horizontal tangent, shouldn't my inverse graph then have a vertical? Oh, so it kind of looks the same. It's going to kind of go like this. I know it's a terrible graph, but that's kind of what the graph of the inverse sine looks like. Oh, okay. Where this is, think of the line y equal x kind of thing. It's just going to do that. Oh, okay. So the graph that I'm looking for isn't actually all that complicated. And by the way, it will pass through the origin, which even makes it easier. So my inverse sine is going to look like this. This. Oh. It's a pretty simple region, isn't it? Okay, so that's what it looks like, because x equals 0 is the y-axis, y equals pi over 2 is a horizontal, and that. Now, it would be useful for me to know what this ordered pair was. Now, let's see. I'm pretty sure I got that one.
1.
How do you know? Because the inverse sine of 1 is pi over 2, because the sine of pi over 2 is 1. So good, Chase. That's useful because I got to set up my limits of integration in a moment. So if I do the arbitrary rectangle, so let's figure out what this looks like. So my ith rectangle looks like top curve, which is pi over 2, minus bottom curve, which would be inverse sine of xi, all times delta xi, and the x values are ranging from what to what?
0 to 1.
0 to 1. Yeah, oh wow, that's beautiful. It's gonna be a piece of cake. So the area is the integral from 0 to 1 of pi over 2 minus the inverse sine of x dx. Great. I have absolute faith that this is the area. So now let's just integrate this. Well, the integral of pi over 2, that's a constant. So it's just going to be pi over 2 times x. And then the antiderivative of the inverse sine function is the antiderivative of inverse sine. Do we have an antiderivative of inverse? Oh, we don't. Oh, darn. I guess we're stuck. Yeah, we are. We can't do this problem. But we can still answer this question. I said it a few minutes ago. Every problem that exists, you can go vertical or you can go horizontal rectangles. Every problem that exists. It's not efficient to do it both ways. What if we tried horizontal rectangles? That doesn't make any sense based on how the problem was asked, does it? But if I went horizontally, right now this is y equals inverse sine of x. Which means it's x equals sine of y. You know what? I think that might be an easier function to deal with. Everything I said is true. Everything I wrote here is correct. But we have a pretty major dead end. You're driving to the grocery store and it turns out the road caved in a mile across. And you're probably not getting across the road today. At least not that route. You got to take a different route. So we're taking a different route right now. This is correct. We just don't know how to do it. Okay, we don't have an antiderivative formula for that function, but we do for the sine function. So let me now, obviously I need a different colored pen. Let's do a new ith area. So how do I measure distance when I'm moving horizontally? Well, when you're vertical, don't you always take the top minus the bottom? Because the top's higher up. So if you're going left and right, which is bigger, the right or the left?
The left.
Which way do numbers increase? Left to right or right to left? I think they increase going down.
Yeah.
So you're going to take the right minus the left or the left minus the right? The right minus the left. Right is always bigger than the, yeah. That's always bigger than that. It's an absolute across the board, no exception. So I'm going to take x equals that minus x equals 0. Oh, I like that one. So this will be x equal the inverse, or excuse me, just the regular old sine of y. And if you want minus 0, delta yi. And the y's are ranging from what to what?
Pi over 2 and 0.
0 to pi over 2. It does matter what order you say it. If you say it in the wrong order, you're going to get the opposite sign, remember. So, can I say the area is 0 to pi over 2 times the sine of y dy? Can I say that? But that's not an x. It doesn't matter as long as those are the same. Heck, what if I made them both t's or q's? Does it really matter what letter of the alphabet these are when I'm integrating? No. Why? Because my final answer is going to be a number. But I could not do this one using vertical rectangles, but I could do this one using horizontal rectangles. What is the antiderivative of the sine function? What function's derivative is
Negative
the sine
cosine.
function? The negative of the cosine. I'm evaluating from 0 to pi over 2. So my answer is the negative of cosine pi over 2 minus cosine of 0, and that answer is when all is said and done, there's nothing left to say or do. It's all been said and done. Come on, don't use your calculator.
-1 with 1.
1. Oh. That creepy looking area with the creepy looking boundaries, the answer is just 1. I tricked you all because I drew a picture that was literally sideways. Here's what I mean. What if I had done y equals the sine wave I want half of the hump of the sine wave. Is this an easy problem? Yeah, you'd all do this and you'd say my ith area is the sine minus 0. I'd integrate from 0 to pi over 2, which is exactly what that one was. What did I do with this? I just flipped it over. Wasn't that sneaky on my part? I gave you something that was a very easy integral in y, but darn near impossible in x. Every function can be set up either way. It is not efficient to set problems up either way. It's only efficient usually in one direction. Okay? But every problem can be set up either way. Let's try another one. If I'm not giving you from x equals to x equals like I did on the very first example, it probably means the curves intersect. Okay. Y equal x squared. What does x equal y squared look like?
The same thing sideways.
This obviously keeps going there, this obviously keeps going there, but my region's going to be in the first quadrant. Okay? I have two parabolas. One's vertically opening, one's sideways. I know that's 0, 0. I'll do that one. What's the other one?
1.
I need two values, so. Anybody tell me without really doing a whole lot of work? Y equal x squared and x equal y squared. So x has to equal x squared and y has to equal y squared at the same time.
1, 1.
Probably 1, 1, yeah. That's not that bad. Now, if I had to solve it, I need to, how would I solve this? Well, over here, I can replace the y with the x squared. Let's do that. So I'd have x equals x squared. Agreed? So that would give me x equals x to the 4th, or I could write it as x to the 4th minus x equals 0, so x times x cubed minus 1 equals 0. So the only real solutions are x equals 0 or x equals 1. This also has two complex solutions. I don't need them. That's a way you can do it algebraically. Or you can just be clever and say, there's got to be 1 more. Okay. Now, vertical rectangles or horizontal rectangles? The answer is yes. Is one going to be easier than the other? No. I said one of the simplest ways that people make their conclusions is if all of my boundaries are given y as a function of x, it's usually easier to just do vertical rectangles. If all of my boundaries are given x as a function of y, then horizontal. What did I do? One of each. So I either have to change one of them, I either have to make this one y's root or make this one x's root. Doesn't matter, it's going to be the same work in the end. My integral is going to look almost identical in the end. Okay? Most people, given the choice, by the way, will go vertical because conceptually it's just easier. When we get into 3D, when you're doing Calc 3 problems, and people can set things up however they want, just so you know, because now they have 3 variables. They always make this the floor and this the ceiling. Everybody does it this way because it's easier to think. Nobody does a problem where what you're finding is sideways, just because it's harder to conceptualize. The math is the same, the answer is the same. But when we're thinking about it, most people would say, you know what, I'd rather go vertical because my brain, this is just easier to picture. And then my integral is going to be with respect to x as opposed to with respect to y. But it actually never matters. Right? It never matters which way I go as long as what I did was correct. So if I go this way, well, clearly that curve is y equal x squared. So what is this curve then?
Square root of x.
Square root of x. Beautiful. Everybody see that? If x equals y squared, then y is the plus or minus the root, but I'm in the first quadrant, so it's the positive root. Okay? So when I set up my integration, my ith area will be, the root is on top, so it will be this minus the parabola, which is on the bottom, and the x values will range from what to what?
0 to 1.
0 to 1. Yes? Good. So area equals the integral from 0 to 1 of what? Do you want to write square root of x?
X to the half.
Let's write x to the half. Minus x squared dx. If you got this far, you're going to get the right answer almost 100% of the time. Only arithmetic errors will slow you down. The whole point of this problem was to get to here. Finishing this should be trivial. When you're answering these types of questions, these are application problems. When you're answering the question and finishing it, you're going to find that the integration itself is probably low level. You're doing harder problems in practice. But I'm going from that question to that integral. Do you see this integral in that question? No, you had to get there. You had to set it up and figure it out. Yeah, you don't see any square roots in that question. But now that I've got this far, the answer should be pretty simple. I do have to integrate correctly, but this integration is fairly low level. So, what's the antiderivative?
2/3 times x to the power of 3 halves.
Good.
Minus 1/3 x cubed from 0 to 1.
Well, I like that. It's just going to be 2/3 minus 1/3, isn't it? Which is 1/3. Pretty nice. We're happy with that. I hope you're happy with that, because that's a good one. Okay. Is this hard overall? No. You're doing integrations that aren't going to be particularly challenging. It's getting to the integrals everything. You don't see the integral in the question. You have to figure it out and set it up. And sometimes, like the one we did over here, sometimes the question is worded in such a way that the problem you did is not the problem you're going to end up doing. So you have to be able to see it both ways. A skill that you will develop over time is you can look at the integral and tell me what the region is. I'm giving you the region and you're telling me the integral. It's much easier that way. It's much easier if I give you all the boundaries and you just set up, okay, here's my integral. But if I give you the integral, can you tell me the boundaries? That's the whole idea. If I started with this integral, then I know that it's the area between these two things from here to here. I can set it up that way. It's kind of nice because it all works very, very well. Okay? Let's do another one. All right. Find the area of the region bounded by y equals e to the x equals 0, y equals 10. And what I would like to do with this one, I would actually like to set it up both ways. Not solve it both ways. I'd like to set it up both ways, with respect to x, with respect to y, as an exercise, if nothing else. First thing, gotta get a good picture here. So e to the x, looks this-ish. X equals 0 is the y-axis, and y equal 10. So have I clearly enclosed a region? Yes. Now, if I didn't know what the original functions were, would you say the setup is just as easy with respect to x or with respect to y? Vertical versus horizontal? Both of them should be relatively simple setups. So I want to do it both ways. So let's start with the vertical. Okay. So the ith area is, well, what's the top curve? That's the line y equal 10. What's the bottom curve? Well, that's the exponential function. And x is ranging from, oh, I don't know what x is ranging from. I'm undoing
Log.
E.
Natural log.
Natural log. Yeah. E to the log, they undo each other. So e to the log 10 is just 10. Is that important? Yeah, again, limits of integration. So if I'm setting this one up vertically, the area is the integral from log 10 to 10 of 10 minus e to the x dx. It is whatever it is. I'm not really all that interested in what the final answer is. I wanted to be able to state it. Did I mess that up?
Wait for vertically.
Oh, I'm sorry.
Yeah,
Zero.
0.
Sorry, I'm looking at the wrong thing. Thank you. This should be 0 to log 10. Thank you, Jason. Now, whatever it is, we'll integrate it and figure it out. I now would like to set it up horizontally. And that is not a trivial thing because my boundaries were not given as x as a function of y. This curve was y equals e to the x. Therefore, it's x equal, the same thing you did over here, x equals
Natural log of y.
natural log of y. Okay? And I can fix this. So in this case, I'll use a different color. My ith area here, right curve minus left curve, so it'd be log yi minus 0, if you will. Delta yi, and the y's are ranging from what to what? Oh, that's not the origin, is it? What is that point right there? It's 0 comma what? 1. 0 comma 1, good, because e to the 0 is 1. So y is ranging from 1 to 10. Oh, the y limits are nicer than the x limits. So can I say it's 1 to 10 of log y dy? Is that correct? What do you think? Log y minus 0, delta y. Beautiful. I know exactly what to do here. The antiderivative of this, let's do it. It's 10x minus e to the x from 0 to log 10. Piece of cake, evaluating that. And of course, the antiderivative of log y is, the antiderivative of log y? We know the derivative, right? Do we have an antiderivative for the log? No, we don't. Kind of like the inverse sine, we can't do this one. Now, this is a problem that the Calc 3 students do. We're not going to do this one, but be mindful that at some point you're going to have to do this one. This problem was presented to you, this problem right here. And you're smart enough to say, I don't know how to do this. In other words, rather than brute force it and do it incorrectly, you're saying, I don't know how to do this. Could you go from this to this, change it to vertical, and get this? Is that possible mathematically? Yes. It turns out to be one of the more important skills. Now, it's not a skill that we develop heavily in Calc 1. By Calc 3, they have to be able to do that for this type of problem. And here's the reason. Okay, I'll give you a really simple reason because it's already come up multiple times. You have a real job. A couple years from now, you're making the big bucks and you're in the engineering world. Nobody's going to hand you a sheet of integrals and say, evaluate all these, turn them in, and then we'll pay you for the week. I want that job, by the way, if it existed. Nope, there's a situation we need you to figure out how to find something. Find a center of mass or find a volume of something. So you have to model it, you have to set it up, you got to do it. You got to create the math, in other words. So you're working with a team of people. Is it realistic that you're going to do the beginning all the way to the end of the problem all by yourself? And just understand the calculus will be a piece of the puzzle. It will never be the entire problem. The numerical answer you get in the calculus sense will be passed on to the next person to work with. In other words, it might be 10% of the overall big picture. A lot of people think we begin and end with the calculus problem. No, it's a piece of a puzzle. But it came to you, your team, and they handed you this integral and said, we're stuck, we don't know what to do. And I don't want to get a decimal value from a computer because I need the exact value because I might use it later. See, if my answer is actually a logarithm, let's say, later on in the problem I might be exponentiating. If my answer were a square root, maybe later in the problem I'm taking a square of it. Often you'll do things that undo. And I will lose the integrity of my answer if I give you a decimal approximation and then I have to manipulate it later. It's amazing how often people will get a wrong answer because they went to the calculator too soon. The final answer to the problem might actually be an integer, but we didn't get an integer because we approximated early on, and then we get further away, not closer. So somebody handed you this problem, and you're saying, this can't be done, I'm going to go backwards, but you weren't given the original problem. Do you understand? You were given what people got to and couldn't go any further, and now it's handed off to you. I've seen this happen more times than I can count in real life. The problem that was handed to you. I've had people contact me and say, you know, I'm a professional, I don't know where to go from this. And I say, well, tell me what you have, we'll set up the problem, and then we'll work backwards and try it the other way. Now, the other way may not be easy, but maybe doing it the other way is possible at least. We reached a dead end. Could we figure out what the region looked like, and then again change the integration to the other way, and then do that problem? That is actually a real life problem that comes up often. And the ability to do that actually trumps your ability to just simply anti-differentiate, doesn't it? It's problem solving. It's the kind of thing you might be asked in an interview, in other words. Wink, wink, nudge, nudge. See, when you're going for that interview, how many are engineering bound here? More than anybody else, okay? That's kind of the most common thing. Any computer science bound? Math. Did I leave something out? What else for this group? Any other majors? Okay, that's pretty much all I see. So let's do the engineering interview because that's most of you. So you're standing there, and of course you brought your transcript because in the interview they really care what your GPA was. I got news for you. When you're filling out those job apps, there's no place on the application where it asks you for your GPA. Strangely enough, they want your degree, probably the institution. They don't really care what your GPA was. Did you graduate? But they're not going to say, oh, your GPA was this, hey, you're in. No, they're going to ask you questions. They're going to ask you to problem solve. And I know this is hysterical, but somebody told me within the last year, they went to the interview and the guy asked the question, they said, hold on, they pulled out their cell phone to Google the question so they could, and the interview ended. Said the interview didn't last 30 seconds. The long board of scary looking people, it was supposed to be like a half hour to an hour interview. The interview lasted 30 seconds because they pulled out their phone. What they're saying is, no, I don't know the answer to any question you could possibly ask me, but I know how to find it on the internet. That's actually what they were saying, and they said they learned a hard lesson. That no, nobody cares how well you can Google something. They asked them a question that they had no idea, and it might not have been something that was easy, but they wanted to see, can you think on your feet? Can you problem solve? Not what did you memorize, but what can you think through? That's the only thing they care about. Can you problem solve? They don't care about your GPA. Can you think on your feet? Can you answer a question? So in realistic situation, what if that was the question? They go, do this. You go, well, I can't do this, but I know how to change the problem, perhaps something I can do. Do you think that would impress them? Oh yeah. Does it even matter what the answer to this question is at that point? Not really, because now you know you could navigate through. I am not going to ask you that question. I do that in Calc 3. But understand that is one of the more important steps along the way. Nobody tells you that now. But when you get to Calc 3, you'll see that that is actually a really important step. Because the concept of it doesn't matter how I set up the problem if my setup is correct. And since there's always two ways to set up every problem, horizontal cuts or vertical cuts, most of the time, one of them is really clear how you should do it. It's not even a question of which way you should go. But then there are times when it absolutely can't make a difference because there was no advantage in either way. A simple rule of thumb, if you can do it in one integral versus two, that's better. If you can have all of your boundaries without having to rewrite them in terms of the other variable, that's better. Because if I gave you boundaries y as a function of x, it may be really difficult, if it's even possible, to turn them around and write x as a function of y. That may not even be something you can do. So that's kind of a way to go. Okay, any questions so far? I'm going to do one more problem before we take a break. And hopefully we can navigate this one to the bitter end. This is gonna be fairly long. Find the area of the region bounded by x equal y squared and y equals x minus 2. Okay? So this isn't too bad. All right. Not great, but it's decent. All right. So like before, I did not give you the boundaries. Can we figure out those 2 points?
Mm-hmm.
How will I do that?
Fucking y squared for x.
Okay, so over here, replace x with y squared. I like that. So y equals y squared minus 2. So how about y squared minus y minus 2 equals 0? Now that's a quadratic. That look okay? So y equals 2 or y equals negative 1. I think that's the negative 1. I think that's the 2. So let's go back to here. If y equals 2, then it appears that x should be, if y equals 2,
Oh.
then maybe x should be, if y equals 2,
4.
then how about, yeah, good,
Yeah.
4. If x is 4, y is 2, okay, that works. I'm checking both of them. If y equals negative 1, then x should be
1.
1. If x is 1, y is negative 1, okay, that works. All right, so when I do this one, and I got, so would that just be y equals square root of x, if it's x equal y squared? Yes, no, maybe?
Mm-hmm.
Yeah, probably. Yeah, it would be. Okay, so let's do that. So, my ith area is top curve to be root xi minus the bottom curve, which was xi minus 2, delta xi. So my area is the integral of this guy minus x plus 2 dx. And of course, the range of values for x is what to what? Well, clearly 4, and what is it on the left?
0.
1. We have kind of an issue here, don't we?
Right under, so.
Does everybody say there's kind of an issue here? That left of this, it's curve to curve. To the right of this, it's line to curve. So I've got line to curve here, which means this is only true from what? 1 to 4. Is this the whole area? Not exactly.
We need to add the 0 to 1 for x to half.
I've got to add, there's a second region here. Yikes. On the left, the top curve we said is y equals root x. What's the bottom curve?
Y equals root x.
Y equals the negative of root x. Not root negative x, the negative of root x. Think plus or minus. Oh, so there's a second, let's call it the jth area, where it's going to be top curve, that's a j now, minus the bottom curve from 0 to 1, as somebody said. Well, that's just, by the way, that's just 2 times the root then, isn't it? So I got to add to this, oh my goodness, to at least I can just double it because it's root minus the negative of the root. So I can double it. Agreed? Whew. Okay. This is gonna be a little bit of a mouthful, but let's do it. So that's x to the 3/2 times 2/3. A half x squared plus 2x, and that's going from 1 to 4, plus that's x to the 3/2 times 2/3. One of the reasons I like using brackets is here's where you actually would use brackets to separate these two. Yikes. Am I gonna have square roots in my answer? Because a half power is a square root. Well, I'm evaluating it at 4 and at 1, which are perfect squares, so I think we're okay there. All right, let's do this on the calculator, shall we? This one's busy. Man, this was huge. This one's huge.
Should have done it right down
Everything we did is correct. Hopefully we get the right answer in the end. We might want to rethink something, but let's finish this one first. So evaluate this at 4, subtract evaluating it at 1, evaluate this one at 1. I don't have to worry about the 0 because it's just going to be 0. Boy, tell me when you get an answer. Everybody should be trying this. I think we did everything right. Pretty sure. You don't actually need a calculator to do any part of this, by the way. You're taking square roots of 4 and of 1, so. Let me know when you got an answer. I can wait.
I got 9 over 2.
You got 9 over 2. Did anybody else get that?
I'm not sure if that's it.
Yeah.
You got 9 over 2. Tell me what you didn't like about this problem. And don't say it because it was long.
There's 2 chunks.
Because I had to do 2 integrations. That's what I don't like about this problem. None of the integrations were hard, but I had to do 2. Now remember I said 1 is superior to 2. And not having to rewrite my boundaries in terms of the other variables is always a good one. Is there something we could have done to make this not as long?
X equals y plus 2, and then solve horizontally.
Let me erase this and there's too much writing, obviously. So we had a sideways opening parabola, and we had a line, and that was what, 4, 2, and that was 1, -1. We had to do separate integrations because if we did vertical rectangles, my vertical boundaries changed to the left of this. Chase says we should go this way. Now, stare at that for a moment. From bottom all the way to top, isn't the left always the curve and the right always the line? So turns out this would have been a little more efficient because I would not have needed 2 integrals. And that really is a governing factor in your choice. I just said it never matters. You're always going to get the same answer, but most of the time one method will be shorter and often less work. So if I went sideways, then this is still x equals y squared. What does this become?
Y plus 2.
X equals y plus 2. So my ith area, sorry, we already know what the answer is, so I'm going to erase all this. So my ith area would be right curve minus left curve. Make sure we subtract in the correct order. So yi plus 2 minus yi squared, delta y, and the y's are ranging from what to what?
-1 to 4.
-1
2.
to 2.
Yeah.
So I can say with certainty, my integral is -1 to 2 of y plus 2 minus y squared dy. Is anyone getting kind of a sense of deja vu here? Does it feel like we've done this before? Have we done an integral that looks like this before? And got exactly 9/2 as an answer?
Mm-hmm.
Could it be that I just took that problem and turned it sideways and asked you the exact same question? Yeah, I did. To show you a really simple point. It never matters whether you go horizontal or vertical, but usually one is significantly less work than the other. Clearly on this one, we went vertical because my boundaries then didn't change. But when I went vertical on this one, my boundaries did change, which made it a much more difficult problem. But if I went horizontal on here, isn't this exactly the integral that gave us, just with x's instead of y's? And we got the same answer, and you're like, oh, that was the whole point. Not that you saw it was the same problem, that was not necessary. But to see that horizontal in this case is superior because it's one integration, I don't have to change, right? It's still y, it's still x equal y squared, and that's, writing this as x equal y plus 2 really wasn't any work. But that problem, doing it that way, was significantly shorter. Plus, did you also notice the types of functions you integrated? They were all polynomials. There were no roots in your answer. You're still going to get the right answer the other way, but when I'm integrating fractional exponents, are there more potential errors? And I'm evaluating, yeah, there's things that can go wrong that really don't need to go wrong. Okay?
How do you know when to use which one?
You have to know what it looks like first. That's why drawing the picture is so critical. If I tried to do this problem without the benefit of a picture, I'm not sure I would get the integration. I mean, I'm pretty good at this stuff, and I wouldn't do this without the benefit of a picture because I don't know where my boundaries are. I don't know which is the bigger, which is the smaller. You say, well, isn't it always obvious? No, don't they change? I mean, because they intersect. They flip places at some point, so that's why I really need to see it. Plus, I need to see where the enclosed region is. Is it possible that I could misinterpret it, maybe do like that region or something over here if I'm doing it without a picture? That's usually what happens is we often choose the wrong region. We choose a region that is unbounded. An unbounded region technically is infinite in area. So that's why I have to know where the boundaries are. Part of the reason you did all the graphing techniques earlier, not just increasing, decreasing and all that, but I kind of need to know what something looks like in order to be able to bound it. Because the next thing we're going to do is we're going to take the shape and then rotate it about an axis to create a three-dimensional object. It's very cool. That's next day. Next day is crazy stuff. Okay, let's go ahead and stop that.
Oh. Yep.
Okay. All right, we're going to
Awesome sauce.
continue. Now I'm going to show you a few little shortcut type tidbits that will help us in the long run that a lot of people don't actually know are there. And so often what we do is we take a problem at face value, we do it the way we're supposed to, and then we find out later, you mean there was a faster way? Sometimes there is a much faster way. So one of the ones I'm going to show you, okay, I'm going to present the problem first. This is just a flat out integral because we're going to use stuff like this all the way through the course. All right, I've got the integral of, how about 4 times the cosine 2x minus, how about 3 e to the 6x, and then plus 8 secant squared 4x. All right. Now, this problem is in every calculus book, and the approach is exactly the same in every calculus book. My argument in each case is not an x, so I'm going to have to obviously do a substitution. But it's different in each problem, so the first thing I'm going to have to do is rewrite this as 3 integrals. So whether this is an indefinite integral or a definite integral, right, I still need to do some form of a substitution. So I'm going to rewrite this as 4 times the cosine of 2x dx minus 3 e to the 6x dx plus 8 secant squared 4x dx. Y'all with me on that? So now we got to do the u sub, but I got to do 3 separate u substitutions because there's 3 separate integrals. Treat them now as completely unrelated. So in this one, I would say let u equal 2x, then my du is 2 dx. Okay? How about the next one? Let u equal 6x, then the du is 6 dx. I'm just going to be lazy. I know I have a number there, but it's just easy to do that right now. And then the last one, let u equal 4x, then my du is 4 dx. So can I now do this as 1/2 times 4? So I have 2 times the cosine u du. And then the next one, minus 1/2 times the integral of e to the u du. And then the next one, plus 2 times the integral of secant squared u du. And now remember, each of these are separate. I probably should have done my u v w just to be, more specific. But I think we all get the point. So what's this one going to be? 2 sine u plus c1 minus 1/2 e to the u plus c2 plus 2 times what? Whose derivative is secant squared?
Tangent.
Tangent plus c3. Now when I go back, this is going to be, the first one was 2x. So 2 sine 2x minus 1/2 e to the 6x plus 2 tangent of 4x. I have plus c1 plus c2 plus c3. If c1, c2, and c3 are all arbitrary constants, and by the way, you have to do different. They cannot possibly be the same. That's actually impossible. It'd be a 1 out of infinity 3 times. So it'd be technically 1 out of infinity cubed. But yeah, if they're all arbitrary constants, can I just call them one big arbitrary constant? Can I just do that? Great. So everything we said was true, everything we said was correct. This is how it's presented in every calculus book, and I never want to see you do it this way. Too long. Way too long. I'm going to show you how to give the answer as the next step. I'm going to show you how to go from question to answer, and you're not going to be skipping a single step. Would you like that one better? Because this is the textbook approach. This is how every human being learns to do this, but it's overkill. Let's remind ourselves of something. If I said I want the derivative of f of kx, where k is any scalar other than 1. Yes, it could be the number 1, but let's assume k is not 1. Okay? I have a constant multiple of x. Then isn't the answer f prime of kx times k? So if I asked you to differentiate, cosine of 10x, you'd say it's 10 times negative sine of 10x. 10 would be my chain rule factor. Well then, what if I want to do this? When I write it as f prime, then you already know the antiderivative is just f. But I can't do this directly. I would have to do this as a u substitution. So I would say, let u equal kx, and then du is k dx. This is what is called a linear substitution. We have done this before. This is, in fact, one of the very first substitution problems I showed you. A linear substitution is different from all other substitutions because your chain rule factor is just a constant. So all I need is a k. Agreed? Then what does this become? 1 over k f prime of u du, which is 1 over k f of u plus c, or 1 over k f of kx. So the antiderivative, that's all I got to do. I just need the 1 over k in front. That's it. So I want to do the antiderivative of the cosine of 10x dx. Is the answer just the sine of 10x?
1/10.
That's it. When your substitution is a linear substitution, then your chain rule factor is a constant, which means there is no time you ever actually have to perform the substitution. You can integrate directly. And this is what I would prefer you to do. Everything we did here was true, everything we did was correct, and 99% of it was an utter waste of our time. What's the antiderivative of the cosine of 2x? It's going to be the sine of 2x times
2.
1/2. The antiderivative of e to the 6x is e to the 6x times 1/6. But I had a 3, so that's a half. The antiderivative of the secant squared, the secant squared of 4x is the tangent of 4x times 1/4. You like that better? That's the way I want you to do it. Same answer? Yeah. What, about 5% of the work? And did we do any formal substitutions? No. There is no need to ever do a substitution when it's a linear substitution. All you need is the chain rule factor. That's what I prefer you to do because it's correct and it's easier. You're not going to make mistakes. You get through faster. And I think it's easier to remember. So the reason I like this problem is I give you a different argument for each of these, but it still didn't require substitution. Now, what if that's not 2x? What if that's 2x squared? Okay, now I need a chain rule factor that involves an x sitting around. That's a completely different animal. Okay? Everybody cool with that one? So when it's a linear substitution, don't actually do the substitution, just integrate. But remember, when you're doing the derivative, you get the chain rule factor as a multiplier. When you're doing the antiderivative, you get your chain rule factor as a reciprocal. That's the big difference, right? And how do I know? Because when I differentiate this, won't I multiply that by k? And then it cancels, and that's how I know I did it right. Okay? That's a nice little tidbit here because it can shorten things. Will you run into things of this nature? Yeah, actually, very often. Now there is another one. I want you to do the following. If I were to write this as a region, what would it look like? Okay, from A to B, this is my function. F of x equals k. K is a constant. What does y equal k look like?
It's a straight line.
Good, horizontal. So this basically looks like a horizontal line, k units high, from. Now stare at that picture for a moment. Would that produce this integral? Right, so I'm going to make my vertical rectangle. Well, y equal k minus y equals 0 from A to B. Okay, good. By the way, what's the area of this rectangle? Wouldn't the area here be k times b minus a? Can I just say this is k times b minus a without doing anything? Feels like I'm cheating. Okay, let's integrate. What's the antiderivative of k dx? It'd be kx from A to B, which would be k times b minus k times a, which is k times. I'd rather just do that. When you are integrating a constant, and you have constant limits of integration, which is actually somewhat common. It's not terribly uncommon. When you're integrating a constant, k, over my constant limits of integration, then you're basically finding the area of a rectangle. That's exactly the translation, which means your answer is going to be k times the difference of these things. You like that one? You should, because it's really simple. So that's another shortcut that you can take. This comes up very, very often, particularly in Calc 3. I would say a huge percentage of the problems that they do, big, gnarly, three-dimensional problems, the last step of the problem will look like this, and they just answer it without any further work. This is absolutely correct, and everything I wrote was correct. But I'm saying that's the answer. I'm telling you, you can go there directly because you can see it. So when you can take shortcuts of that nature, you're not cheating. You're like, I already know what the answer looks like. You can't do this very often, but if it's a constant, you can. So let's do something that's just downright scary. All right, I'm going to find the area of the region bounded by y equals x secant squared x squared, comma, y equals 0, that's the x-axis, x equals the square root of pi over 3, and x equals the square root of pi over 4. I could have just said square root of pi all over 2, but it's easier to write that. Yikes. Yikes. Don't have any idea what that looks like. Here's the cool thing. I don't need to know what that looks like. Okay. Are these two positive numbers?
Yeah.
Everybody agree those are both positive numbers? Which one's bigger? Smaller denominator, bigger number. Okay. I don't know what they are, but I know they're both positive. So let's just say that's the square root of pi over 4, and that's the square root of pi over 3. How's that? Like that. Now, between these two values, by the way, secant is never 0. Cosine is 0. Secant is never 0. So the secant function is either positive or the secant function is negative. It's never 0. You with me? So tell me about secant squared. It's always positive because I'm being squared. I have no idea what secant squared looks like. So here's what I'm going to do. There's my secant squared. I don't need to know what it looks like. It's above the x-axis. Are you okay with that? That's all that matters. It's above the x-axis. If the secant can't be 0, then it's not crossing over the x-axis. And the secant squared you just said is always positive. Do I need to know the exact value or the exact shape of the curve on top? No. I just need to know that that curve is above the x-axis. So when we do this problem, okay, we're going to set it up like this. So what's my ith area? It's going to be that times that, and x is going to range from the square root of pi over 4 to the square root of pi over 3. That just looks terrifying, doesn't it? I said the region, you have to have everything in the right place. You have to have your boundaries correct. I need to know what's on top, what's on the bottom, what's on the left, what's on the right. Have I correctly stated that? Yeah. Is my picture accurate? Not even a little bit. Does it matter? No. I just need to know the secant squared is above the x-axis, because I'm not going to actually draw the graph. I know the secant squared isn't down here, so I know it's above here. So I did that. Now let's write the integral. So the area equals the integral from the square root of pi over 4 to the square root of pi over 3 of x secant squared of x squared dx. Man, that looks terrifying. Do you want to do this as a substitution? No, what's your argument here? X squared, and you have a product, which we don't know how to integrate a product, but my argument's x squared, so maybe that other x is a chain rule factor. You think maybe? So should we do a substitution? Yeah. What's u going to equal?
X squared.
X squared. What's my du?
2x.
2x dx. Well, I'm almost there. Okay.
Change limits.
Dude, those limits are terrifying. I mean, I got square roots of pi's. I mean, who would think of such a thing? Well, me, but I mean, really, who would think of such a thing? All right, so as x is going from the square root of pi over 4 to the square root of pi over 3, then u is going from, oh wait a minute, u is x squared, isn't it? So what's u going to go from?
Pi over 4 to pi over 3.
Oh. That doesn't look as scary now, does it? Here's over here. So what's my new integration then? It's 1/2 the integral from pi over 4 to pi over 3 of secant squared u du. Oh, can we do that?
Mm-hmm.
What would that be?
Pi over 4 to pi over 3 of.
What do we, what's the antiderivative?
10.
Tangent u. Hmm. So that's 1/2 tangent pi over 3 minus tangent pi over 4. Now, I'll just walk away because I have no idea what those are. Oh, wait a minute. Do we know what those are? Yeah, those are common angles. There is a gimme there. Which one's the gimme? What's the slope of a 45
Pi over
degree
4
line?
is 1.
1. That's what that means. That's the slope of a 45 degree line. That's the slope of the 60 degree line. It's a common angle. We actually should know that one. Can I improve upon that? Is there any advantage to saying root 3 over 2 minus 1/2? Nah, I'll probably just leave it alone. Wow. The original question looked absolutely terrifying, didn't it? But the answer doesn't look not that big a deal because we were able to do the substitution. Now, here's the main thing I wanted you to see here. I don't need to know what it looks like. What if this was a slightly more complicated problem and maybe I don't know if this crosses the axis or not? Okay? There's stuff going on, maybe I don't know. Hold on. Here we go. Oops. Not okay. Oh. Got it sooner than usual. All right. Oops. Hold on. Okay. Would you say that's scary looking?
Hmm.
What was our, can somebody give me a rough decimal approximation of the two values? The square root of pi over 3 and the square root of pi over 4? Just give me loose decimals. This is 1 point what?
Oh, that one.
1.0233.
Okay, that's good enough. How about this one?
0.886.
Okay. So you're kind of right in here. Okay, you're kind of right in there.
Mhm.
So did it matter what my graph looked like? No, it was above the x-axis. That's all that mattered. If I really, really want to get strict and, I could do this. I have a graph, I truly have no idea what it looks like. And I'm trying to set up my boundaries, but I don't know which one's on top because I don't know what the graph looks like. Can I look at the graph on Desmos?
Hmm.
Will that help me determine which one's on top and bottom? Now, it won't help me with things like my limits of integration and my intersections, but if I didn't know which one was on top, if I say find the area bounded by, and you think you set it up perfect, and then your answer is negative, assuming your calculus, you didn't make any mistake, it means you have the wrong curve on top and bottom. We need to, but I didn't know what it looked like in the first place. So that's where I would use something like Desmos. All I cared about was, right, it's above the x-axis. Okay. And also it's being squared, so again, now, you notice that the curve itself dipped below the x-axis, but when did it dip below the x-axis? Only when x was negative. Secant squared is never negative, but the x is what may have been negative, okay? So that's why it's totally okay. And again, we were going over here, so it didn't matter that it was touched. So I just wanted to show you that you could always look at the picture if it really, really mattered. In this case, it really doesn't matter. Okay, any question on that one? That one seemed absolutely terrifying because you don't know what it looked like, but in actuality, the integration was just a simple substitution. Okay, and that's kind of important. All right. Let's do another one. This one, a picture will be very useful. Okay. Well, I know what a cosine wave looks like. In fact, I'm going to loosely do this. That's y equal cosine. I said y equal cosine plus 2. What is that going to do to this graph?
Move it up 2 centimeters.
It's going to move it up 2 units. So I'm really happy with my cosine curve. I just don't know if I can do another one that's good. So what can I do with my x-axis? Bring it down 2 units. True laziness. Isn't that -1?
Mm-hmm.
This is, right, this is y equals 0 now. Okay, so I want to raise everything, so that should be 3, shouldn't it? Let me do this. I think I got that more or less. My scale's a little off, but you get it? I just raised my cosine graph up 2 units. So this used to be 1, now it's 3. This used to be -1, now it's +1. This used to be 0, now it's 2. Okay? I don't really need that, but I want to make sure I have my picture correct. Now, I said from -π/2 to π/2. Where's the -π/2? So far, so good? Is this pretty clear that I want to go vertical rectangles? Could I do horizontal? Yes. I don't want to, but if I did, then basically I have this box, that's easy. That one's easy, and then I would do this. But the problem is I'd have to write x in terms of y, which means I'd have inverse cosine. And I'd be integrating inverse cosine. Remember the problem we ran into before with inverse sine? We don't know the antiderivative. I could absolutely set up the integral with horizontal rectangles, and it'd be fairly simple to set up. And then I'd wave at it as I walked away to the next problem because I can't do anything with it. So we want to do vertical rectangles here because we want to actually give an answer. So if I draw an arbitrary rectangle, yeah, that's pretty straightforward. My ith area is simply going to be the cosine of xi plus 2 delta xi, and the x's are going to range from negative pi over 2 to pi over 2. So far, so good? Yes? No? Maybe? I think. So my area equals. Okay, before I do another thing, any observations? Anybody paying attention? We're not sleeping our way through life here. What do you notice about that integral? Do you notice anything?
Symmetrical?
Well, my limits are symmetric, aren't they?
Yeah.
Huh. If your limits are not symmetric, you don't do anything, you just move on. My limits are symmetric.
You can do 2 times 0 to pi over 2.
Well, back up. Is this function odd or even?
Yeah.
Well, if it were an odd function, then half of it would be above the x-axis, half of it would be below, and I'd have that rotational thing. Now, this doesn't look rotational, but does this look maybe like a mirror?
Mm-hmm.
Is the cosine an even function? Yes, it is. Is a constant an even function? Yes, because it's technically 0 degree. Think of it as x to the 0th power. That is absolutely an even function. Therefore, what can I do, Chase?
Make it 2 times integral from 0 to pi over 2 of then, so cosine x plus 2.
I would strongly suggest doing this for 2 reasons. Okay? Anytime you have an even function and you double it, it's going to be less evaluating overall. But the primary reason is when you evaluate, the antiderivative of an even function is an odd function. And when you evaluate the odd function at the negative limits, sometimes we make boo-boos there. But when you evaluate an odd function at 0, it is always 0. So you just eliminated half of the evaluation because when I evaluate the antiderivative at 0, it's already going to be 0. I know this. That's one of the really important properties. So I'm not making more work by doing this extra step. I'm actually eliminating half of the work of the entire problem. I'm a big fan of that. What's the antiderivative of the cosine function?
Sine x plus 2x.
Now, quick notice. Sine of 0 is 0, 2 times 0 is 0. That's what I'm referring to. But if I evaluated those at the negative, then we sometimes have some issues. So, let's keep going. This is 2 times,
1 plus pi.
the sine of pi over 2 is 1.
So pi. So 2 plus 2 pi.
Not bad. Now, this is the first time today we've used symmetry in an answer. If symmetry is appropriate to use in the answer, you want to use it. Okay? You're not going to see it all that often, but occasionally. In this one here, again, because of my setup, what if this was not symmetric? What if I did this for the sine wave? So I want to do that because I want to show you where you can be lazy. I want the exact same problem, but I want it for the sine wave. And I want to do y equals the sine of x plus 2. Okay, so we'll do just like we did a moment ago. Okay, and so what I want to do is move my axis down 2 units. So now it's right there. And I want to go from here to here. Well, it's pretty obvious there's no symmetry in this picture. Agreed? That doesn't look like anything. So my ith area, same problem exactly, from negative pi over 2 to pi over 2. My ith area is the sine of xi plus 2 delta xi, and once again, negative pi over 2 to pi over 2. So when I write this integral, my area is from negative pi over 2 to pi over 2 sine x plus 2. I have shown you all of the shortcuts you need in life to get through this problem. I have symmetric limits. Is this an odd function? No. Is this an even function? No. My first term is odd, my second term is even. Oh darn. Wait a minute, I showed you a trick last day. What can you do? We did this problem last day, not this exact problem. I gave you odd and even mixed on symmetric limits. Do you remember what you did? Excuse me. You separated them. Is this legal, first of all? Yes. Why would I do such a thing? What's this?
0.
Odd function symmetric limits. Oh. What's this? What's pi over 2 minus negative pi over 2?
0.
Pi over 2 minus
pi.
negative pi over 2. What's the length of that interval?
Pi.
Pi.
2 pi.
Remember I said about integrating a constant? That's the answer to the question. That piece was 0, that piece was 2 pi. Now, did I have to do this? Absolutely not. No, I could have done this. I could have done this. There's nothing wrong with doing this. But this is easier. It's also faster. If I split this up and use the fact that I know that that's an odd function, I didn't even have to integrate it. That's automatically going to be 0. An odd function over symmetric limits, we proved last day, is always 0. An even function over symmetric limits is just 0 to upper limit and double. That's by far more common. But this is the one that comes up occasionally. I did an example last day where I used a polynomial with symmetric limits. The polynomial was neither odd nor even. But because it was symmetric limits, I pulled it apart. I kept the odd terms and the even terms separated. That's what you really want to do in this case. Because in the odd part is automatically 0, I don't have to integrate it. And the even, I go to upper limit and 0 to upper limit and double it. Less work. And in this case, because it was a constant, it's just a constant times the length of the interval, which is pi. So like I said, if there are shortcuts, I'm going to show them to you. But there may not be shortcuts for everything. Take advantage of shortcuts when they come around. You don't have to. But if you do, then sometimes things are easier. But it also is an indication that you really understand them. Let's go back to the beginning of the course. Literally, third day of class when we were looking at limits as x goes to infinity for rational functions. I proved for rational functions, if I multiply the numerator and denominator by 1 over x to the larger power on the bottom, and then did all that, we got all the transient terms, remember, we did all this stuff, and in the end you said, oh, all I really have to do is look at the degrees. If it's a limit to infinity on a rational function, higher degree on top, it's going to infinity, higher degree on bottom, it's going to 0, same degree, it's going to lead coefficients, quotients. We proved that. So when I asked that question, you could do all of the algebra, get the transient terms, and take the limit. That's absolutely correct. Or you could just use degree in your argument. Which do you think I preferred you did?
Use degree.
Yeah. It's absolutely clear and you got there faster. And there's no chance you're going to make a mistake. Now, when it wasn't a rational function, maybe we had roots involved and stuff. No, that's when I had to multiply top and bottom and manipulate and play with things. But you deal with rational functions all the time. And those limits to infinity, we might as well take advantage of it. Okay? And use the degree argument because it is a strong indicator that you absolutely understand what's going on and you understand how fast you can give an answer. And you're justifying your answer with just one simple statement, like degree of the numerator is greater than the degree of the denominator. So this problem here, you did not have to take the shortcut. But if you take the shortcut, it's clear understanding, that, or indication, I should say, on your part, that you understand this at a slightly deeper level. Otherwise, you're just mindly going through all of the steps, and at the end of the problem, you say, oh, you know, I could have made this a lot easier. Right? So I'm hoping that you do that, but that just takes practice. You just got to do a bunch of problems. That's it. Okay, let's go and stop. We have